Hello, Chem 20s. It's Mr. Jukley here, and we've actually got our last lesson for our solutions acid-base unit, which is kind of cool. We were talking about acid-base indicators, some of which you're actually already familiar with, like litmus and stuff like that. Anyways, before we jump in, I'll just mention that this is actually going to be divided into two sort of chunks here. So I'm going to do this on the smartboard, and it's the lesson proper, I suppose. And then I'm actually going to create a second video on my phone in the lab and show you what this would look like in a lab situation. So one lesson in two parts. Anyways, let's jump in. So acid-base indicators change colors depending on when they're with acids or bases. That's kind of the thing that we know about. That's what we talk about with litmus, right? Litmus is red with an acid and blue with a base. That being said, not all litmus are like distinct. 7 and below are acids, or sorry, change color right at a pH of 7. So yeah, that's what we're looking at today. Okay, most indicators exist in one of two forms, and they're very different in color. Again, litmus, red versus blue. There's some indicators that go through even more changes than that, but we're focusing primarily on the ones that have two distinct colors. And then those two distinct colors depend on, again, the acidity of the solution. Not necessarily whether they're an acid or a base, but the acidity of a solution. Acid-base indicators kind of have complicated formulas and sometimes their names as well, so often they are abbreviated. You can actually see these abbreviations and their names as well on page, oops, what page is this in our data booklet? Page 10 in our data booklet. Page 10. So if you don't already have your data booklet, you probably want to check this out. So let's go through and let's see the general idea first. Okay, the general big idea. So when something is in its lower pH form, so lower pH typically means acidic form. That being said, it doesn't necessarily need to be an acid. It's just in the thing that is more acidic. It's generally abbreviated as HIN, where H tells us that it's an acid because acids typically have H in them, and IN is just short for indicator, so acid indicator. The base one, so the higher pH, or sometimes known as the base form, is written as IN negative. So IN negative, so it's an indicator and it's a negative, and we learned in previous lessons that a negative is a space for a hydrogen to attach, which would create a base. Right? So if you see the H, that's the lower pH value, more acidic. If you see the negative, that's the higher pH or more basic. Cool. So we're going to use the indicator, bromothymol blue, to start things off, and we're going to represent it in both its acidic form and its basic form. So if we find this on our data booklet, we're looking for bromothymol blue. Bromothymol blue, there it is. So in its more basic form, it's HBB. In its, sorry, I said that wrong, acidic form, it's HBB. In its more basic form, it's BB negative. So basic, and I know that it's basic because it's got the negative symbol. So basic, perfect. And we're looking at the pH ranges for this. So in its acidic form, it would be yellow. So in its acidic form, it's got a pH of less than 6. In its more basic form, it's got a pH of greater than 7.6. So basic form, pH greater than 7.6, and it would turn blue. Okay, so we're looking at this, and they all line up. So acid, base. So again, acidic symbol, HBB, acidic pH range is less than 6, and acidic color is going to be yellow. For basic, I'll use a different color to highlight. For the basic side of things, the symbol is BB negative, the pH range is greater than 7.6, and the color, when it's in a solution greater than 7.6, would be blue. So B for base, and you see all of the green things there that correspond to the base. Any ideas what it would look like if we put it in a solution between 6 and 7? Be a mixture of the yellow and blue. And yeah, a mixture of yellow and blue is typically green. Cool. So as we go through, we want to use our pH chart. And this is let's just go back to a nice skinnier felt pen here. Our pH chart, it is not on the back of our periodic table. That's old and I forgot to change it, so you can scribble that out. It's actually page 10 of our data book, and you should probably already be there. So let's look at methyl orange as an example. So with methyl orange, if the pH is less than 3.2, the color is going to be red. If it's greater than 4.4, it's going to be in its more basic form, and the color is going to be yellow. Cool, and then if it's between 3.2 and 4.4, the color is going to be a mixture, it's going to be orange. So let's check that out. Methyl orange. You see methyl red? Here's methyl orange right here. So I'm looking at methyl. Let me zoom in on this a little bit more here too. There we go. So I'm looking at methyl orange. Here it is right here. So I've got the more acidic form, I've got the more basic form, or low pH, high pH. It tells me that my pH range is 3.2 to 4.4. So 3.2 is on my more acidic side, and 4.4 is on my more basic side. Then it goes through, and the next thing it tells me is the red corresponds to anything less than 3.2. So if I put methyl orange in something that had a pH of less than 3.2, it would turn red. If I put it into something with a pH of more than 4.4, it's going to turn yellow. And if it's somewhere in between 3.2 to 4.4, it's going to be orange. It's going to be the mixture. Cool. That's our first one. The second one, phenolphthalein. Let's forget about this and let's just look at our data booklet here. Phenolphthalein. Phenolphthalein is way down here. It is for typically stronger bases. Let me clean up all this other stuff so we can really focus on phenolphthalein. Okay, so phenolphthalein, in its acidic form, its more acidic form, which is anything with a pH less than 8.2, it's going to be colorless. In its basic form, which in this case is anything with a pH of greater than 10, it's going to turn pink. And then in the middle, it's going to be very, very, very faint pink. Cool. Let's see, what else do we got here? Bromothymol blue. So in this case, now it tells us 1, 2, 3. So the pH range is 6.0 to 7.6. So what would it look like if my pH was less than 6, greater than 7.6, or in the middle between 6 and 7.62. So let's go back to the data table. Actually, let me double check. Bromothymol blue. We may have already used this as an example now that I'm thinking about it, but that's okay. Bromothymol blue. So its acidic form, which is a pH of less than 6, it's going to be yellow. In its basic form, which is a pH of greater than 7.6, it's going to be blue. And then in the middle, it's going to be a mixture. So pH of 1 is going to be yellow, or sorry, the color, sorry, of number 1, representing the acidic color, while the pH of 2, let's see, is going to be green, so right in the middle, so green. And then the base color is going to be 3, which is going to be blue. Cool. I hope that kind of made sense for people. So let's look at this in a little bit more detail. I'm going to get you to put the video on pause and play and stuff like that here. We're going to do some of these questions together, and then you'll have a bit of homework. So for this first question, according to the table of acid-base indicators in the data booklet, what is the color of each of the following indicators in the solution of given pH? So phenolphthalein, 11.7, bromothymol blue, 2.8, litmus, 8.2, and methyl orange in a solution with a pH of 3.9. Go ahead, put the video on pause, see if you can figure out what each color will be for each indicator in each solution. Put the video on pause, and as soon as you're ready, we'll get going again. Alrighty, so I've got my answers up here. I've got phenolphthalein with a solution of 11.7. Let's just double check. Phenolphthalein is right here. 11.7, that's more on the base side of things. That means it's going to be pink. Nice. Bromothymol blue with a solution of 2.8. This is getting messy. Let's clean this whole thing up. Bromothymol blue is right here With a solution of 2.8, well, that's way less than 6, so it's going to be yellow. Nice. I think litmus is a little bit trickier. It's not actually in the list, but we know that litmus turns at approximately a pH of 7, turns from blue to red. Litmus, you probably remember from other courses, if it's in a base, it's going to be blue. And then finally, methyl orange with a pH of 3.9. So let's just check out methyl orange. Oh, I got it all highlighted and stuff here. So I think it was a pH of 3.4 or 3.9 or something like that. Doesn't really matter. It's right in the middle of this range. So somewhere between red and yellow is orange. Nice. Okay, so there's that one. Let's flip the page. Let's have a look at this next one. Same idea, just a little bit different way of looking at it. So complete the analysis for each of the following diagnostic tests. If it's added to the solution and the color of the solution turns, well, whatever it says right here, what is the pH range? So we're not looking for a specific pH, like 6.2. We're looking for the range that it could be. So I'll do the first one with you, and then I'll get you to put it on pause and check out the other one. So we got methyl red is red. So let's go back here. Methyl red, where's methyl red? First off, let's clean up. This is a huge mess. Methyl red is red. Just trying to keep it in my mind here. So methyl red is red. That means it's on the more acid side of things, and the more acid side of things corresponds to that, 4.8. So it has to be less than 4.8. So less than 4.8. Perfect. I hope you got the idea. Again, put the video on pause here. I'm going to do the exact same thing and see if you can figure out the others. Unpause when you're ready to go. Go for it now. Okay, so I think I've got mine good to go here. So alizarin yellow, if it's red, that means the pH must be greater than 12. So remember the little thing. So if I've got pH, the open side of this little Pac-Man piece means this is the bigger side and this is the smaller side, so greater than 12. For bromocresol green, if it is blue, the pH has to be greater than 5.2. And then for bromothymol blue, it's green. Well, that means that it's somewhere in the mixture here, so the pH has to be somewhere between 6 and 7.7. Cool. Okay, let's see. Measuring pH. This whole thing says here, this whole big thing, all it says is that we can use a bunch of different indicators to estimate the pH of particular substances. Okay, so if we know that some of them have to be higher than this, some of them have to be lower than this, we can use it to estimate. Let's check it out. Let's just see it in action here. So question number 3, we got separate samples of an unknown solution turned methyl orange and bromothymol blue yellow. They turned bromocresol green blue. Okay, so here is our evidence for this. So methyl orange is yellow. Let's see what that actually means. Methyl orange, here's methyl orange. It says that it's yellow. So that means that the pH has to be greater than 4.4. So greater than 4.4. Nice. Okay, bromothymol blue is yellow. Let's go back here. Bromothymol blue, here it is. It says that it is yellow, so that means it has to be less than 6.0. So less than 6.0. We've already got a pH range here, so it's got to be greater than 4.4, but less than 6.0. Let's see if this last thing, bromocresol green, let's see if it being blue tells us a little bit narrower range. So bromocresol green, that's what it was, right? Bromocresol green was blue. Where are we here? There it is. Bromocresol green. It was blue, which means that the pH has to be greater than 5.4. So let's go back to here and let's say greater than 5.4. Now, all we're really doing with all of this section is we're trying to check out the narrowest range. So the pH has to be greater than 4.4. It also has to be greater than 5.4. So I'm just going to put the pH has to be greater than 5.4. Right? Because if it's greater than 4.4, it's also greater than 5.4. And then it has to be less than 6. So the pH has to be less than 6. That means our pH range has to be 5.4 to 6.0. There's our pH. That's a fairly narrow pH range as well. Let's see. Question B says calculate the approximate hydronium ion concentration. Oh, well, we can do that. So I know that concentration of H3O is equal to 10 to the power of negative pH. So if I'm looking for the range, I do 10 to the power of negative 5.4, get my answer. 10 to the power of negative 6.0, get my answer. And then that would give me a range, I believe, and you can try this one out on your own too. That range is from 3.98 times 10 to the negative 6 all the way up to 1.0 times 10 to the negative 6. And of course, that would be moles per liter. That kind of looks like a minus sign, so I'm going to write the word 2 instead. Cool. So that's one way to estimate it. Sometimes on multiple choice stuff, you see an appropriate pH could be, say, 2.8 times 10 to the negative 6, and that's, that's what you would choose. It's between those two. Cool. So question 4, I'll just get you to think about it. If you want to try this out, that's okay, but you don't have to. So solving puzzles is a common feature of scientific enterprises. The Science Olympics actually does this one. Design an experiment uses indicators to identify which of the solutions has a particular pH. So if you want to try that out, you've got three unknown solutions, X, Y, and Z, and then you know the pH, but you don't know which pH belongs to which unknown. Could you design an experiment that uses indicators to figure that out? Again, if you want to, go for it. If you don't want to, don't worry about it too much. What you should be looking at here, and I circled a couple questions. Let me just find them here. Questions 1, 6, and 7, 6, 7. Those ones are really, really good questions. The rest are all bonus material, and there's quite a bit here, so if you want to go through it in lots of detail, you want to go through all of them, go for it. But 1, 6, and 7 would be the minimum that I'd hope people would look at. And I'll just give you a quick hand with question 1, at least part of it, so you get the idea. So remember, when I say acid color, acid pH range, it doesn't necessarily need to be an acid. It's just the acid side of things. So alizarin yellow. Let's go back over here and let's look at alizarin yellow. Let me just clean everything up. And then we need to find alizarin yellow. Where is it? Where is it? Ah, there it is. Alizarin yellow. Too thick of a felt pen, though. So its acid color and its acid range is anything less than 10.1. Remember, so it could be 9. 9's not an acid, but it's on the more acidic side of things, whereas the 12 is on the more basic side of things. So its acidic form is going to be yellow, its basic form is going to be red. Let's go back and have a look at that. So its acid color in its acidic form is going to be yellow. Better double check that. Yes, yellow. Its base color is going to be more red. The acid pH range was anything less than, so you can write the pH was less than 10.1. Let's see. The intermediate color, well, that's between yellow and red. That's got to be orange. The pH range would be 10.1 to, where is it here, 12.0 for the intermediate pH range. And then the base color range must be anything, so with a pH greater than 12. Cool. So again, 1, 6, and 7 are your basics. The more you practice with this, the easier it's going to get. I'll leave it there for now, and I'll go have a quick look at this lab video right away. Bye for now.